All right, so we'll try to finish the rest of this uh, notebook, which has convolutions and ResNets. And there are also a couple of bonus exercises. I would like to do them, but I'll just try to finish and build ResNets in this video. All right, so let's get into it. This section is light on exercises. Surprisingly hard to implement convolutions from scratch. Okay.
Suppose I give you two different lists of numbers, or maybe two different functions, and I ask you to think of all the ways you might combine those two lists to get a new list of numbers, or combine the two functions to get a new function. Maybe one simple way that comes to mind is to simply add them together term by term. Likewise with the functions, you can add all the corresponding outputs. In a similar vein, you could also multiply the two lists term by term and do the same thing with the functions. But there's another kind of combination just as fundamental as both of those, but a lot less commonly discussed, known as a convolution. But unlike the previous two cases, it's not something that's merely inherited from an operation you can do to numbers. It's something genuinely new for the context of list of numbers or combining functions. They show up all over the place. They are ubiquitous in image processing. It's a core construct in the theory of probability. They're used a lot in solving differential equations, and one context where you've almost certainly seen it, if not by this name, is multiplying two polynomials together. As someone in the business of visual explanations, this is an especially great topic, because the formulaic definition, in isolation and without context, can look kind of intimidating, but if we take the time to really unpack what it's saying, and before that, actually motivate why you would want something like this, it's an incredibly beautiful operation. And I have to admit, I actually learned a little something while putting together the visuals for this project. In the case of convolving two different functions, I was trying to think of different ways you might picture what that could mean, and with one of them I had a little bit of an aha moment for why it is that normal distributions play the role that they do in probability, why it's such a natural shape for a function. But I'm getting ahead of myself, there's a lot of setup for that one. In this video, our primary focus is just going to be on the discrete case, and in particular building up to a very unexpected but very clever algorithm for computing these. And I'll pull out the discussion for the continuous case into a second part. It's very tempting to open up with the image processing examples since they're visually the most intriguing, but there are a couple bits of finickiness that make the image processing case less representative of convolutions overall, so instead let's kick things off with probability. And in particular, one of the simplest examples that I'm sure everyone here has thought about at some point in their life, which is rolling a pair of dice and figuring out the chances of seeing various different sums. And you might say, not a problem, not a problem. Each of your two dice has 6 different possible outcomes, which gives us a total of 36 distinct possible pairs of outcomes. And if we just look through them all, we can count up how many pairs have a given sum. And arranging all the pairs in a grid like this, one pretty nice thing is that all of the pairs that have a constant sum are visible along one of these different diagonals. So simply counting how many exist on each of those diagonals will tell you how likely you are to see a particular sum. And I'd say, very good, but can you think of any other ways that you might visualize the same question? Other images that can come to mind to think of all the distinct pairs that have a given sum? And maybe one of you raises your hand and says, yeah, I've got one. Let's say you picture these two different sets of possibilities each in a row, but you flip around that second row. That way, all of the different pairs, which add up to 7, line up vertically like this. And if we slide that bottom row all the way to the right, then the unique pair that adds up to 2, the snake eyes, are the only ones that align. And if I schlunk that over one unit to the right, the pairs which align are the two different pairs that add up to 3. And in general, different offset values of this lower array, which remember I had to flip around first, reveal all the distinct pairs that have a given sum. As far as probability questions go, this still isn't especially interesting because all we're doing is counting how many outcomes there are in each of these categories. But that is with the implicit assumption that there's an equal chance for each of these faces to come up. But what if I told you I have a special set of dice that's not uniform? Maybe the blue die has its own set of numbers describing the probabilities for each face coming up, and the red die has its own unique distinct set of numbers. In that case, if you wanted to figure out, say, the probability of seeing a 2, you would multiply the probability that the blue die is a 1 times the probability that the red die is a 1. And for the chances of seeing a 3, you look at the two distinct pairs where that's possible, and again, multiply the corresponding probabilities, and then add those two products together. Similarly, the chances of seeing a 4 involves multiplying together 3 different pairs of possibilities and adding them all together. And in the spirit of setting up some formulas, let's name these top probabilities A1, A2, A3, and so on, and name the bottom ones B1, B2, B3, and so on. And in general, this process, where we're taking two different arrays of numbers, flipping the second one around, and then lining them up at various different offset values, taking a bunch of pairwise products and adding them up, that's one of the fundamental ways to think about what a convolution is. So just to spell it out a little more exactly, through this process, we just generated probabilities for seeing 2, 3, 4, on and on up to 12. And we got them by mixing together one list of values, A, and another list of values, B. In the lingo, we'd say the convolution of those two sequences gives us this new sequence, the new sequence of 11 values, each of which looks like some sum of pairwise products. If you prefer, another way you could think about the same operation is to first create a table of all the pairwise products, and then add up along all these diagonals. Again, that's a way of mixing together these two sequences of numbers to get us a new sequence of 11 numbers. It's the same operation as the sliding windows thought, just another perspective. Putting a little notation to it, here's how you might see it written down. The convolution of A and B, denoted with this little asterisk, is a new list, and the nth element of that list looks like a sum. And that sum goes over all different pairs of indices, I and j, so that the sum of those indices is equal to n. It's kind of a mouthful, but for example, if n was 6, the pairs we're going over are 1 and 5, 2 and 4, 3 and 3, 4 and 2, 5 and 1, all the different pairs that add up to 6. But honestly, however you write it down, the notation is secondary in importance to the visual you might hold in your head for the process. Here, maybe it helps to do a super simple example, where I might ask you what's the convolution of the list 1, 2, 3 with the list 4, 5, 6. You might picture taking both of these lists, flipping around that second one, and then starting with it slid all the way over to the left. Then the pair of values which align are 1 and 4, multiply them together, and that gives us our first term of our output. Slide that bottom array 1 unit to the right, the pairs which align are 1, 5, and 2 and 4, multiply those pairs, add them together, and that gives us 13, the next entry in our output. Slide things over once more, and we'll take 1 times 6 plus 2 times 5 plus 3 times 4, which finally the last term will look operations, and you can confirm I'm not lying to you. If you take the convolution of 1, 2, 3 against 4, 5, 6 probability distributions, both that you'll get. We've seen one case where this is a natural and desirable operation, adding up two probability distributions, and another common example would be a moving average. Imagine you have some long list of numbers, and you take another smaller list of numbers that all add up to 1. In this case, I just have a little list of 5 values, and they're all equal to the beginning of it. Once our smaller list of values entirely overlaps with the bigger one, think about what each term in this convolution really means. You're taking an average of your data inside this little window. Overall, the process gives you a smoothed out version of the original data. And you can modify this starting with a different little list of numbers, and as long as that little list all adds up to 1, you can still interpret it as a moving average. In the example shown here, that moving average would be giving more weight towards the central value. This also results in a smoothed out version of the data. If you do kind of a two-dimensional analog of this, it gives you a fun algorithm for blurring a given image. And I should say the animations I'm about to show are modified from something I originally made for part of a set of lectures I did with the Julia Lab at MIT for a certain open courseware class that included an image processing unit. There we did a little bit more to dive into the code behind all of this, so if you're curious, I'll leave you some links. But focusing back on this blurring example, what's going on is I've got this little 3x3 grid of values that's marching along our original image. And if we zoom in, each one of those values is 1/9. And what I'm doing at each iteration is multiplying each of those values by the corresponding pixel that it sits on top of. And of course, in computer science, we think of colors as little vectors of 3 values, representing the red, green, and blue components. When I multiply all these little values by 1/9 and I add them together, it gives us an average along each color channel, and the corresponding pixel for the image on the right is defined to be that sum. The overall effect, as we do this for every single pixel on the image, is that each one kind of bleeds into all of its neighbors, which gives us a blurrier version than the original. In the lingo, we'd say that the image on the right is a convolution of our original image with a little grid of values. Or more technically, maybe I should say that it's the convolution with a 180-degree rotated version of that little grid of values. Not that it matters when the grid is symmetric, but it's just worth keeping in mind that the definition of a convolution, as inherited from the pure math context, should always invite you to think about flipping around that second array. If we modify this slightly, we can get a much more elegant blurring effect by choosing a different grid of values. In this case, I have a little 5x5 grid, but the distinction is not so much its size. If we zoom in, we notice that the value in the middle is a lot bigger than the value towards the edges. And where this is coming from is they're all sampled from a bell curve, known as a Gaussian distribution. That way, when we multiply all of these values by the corresponding pixel that they're sitting on top of, we're giving a lot more weight to that central pixel, and much less towards the ones out at the edge. And just as before, the corresponding pixel on the right is defined to be this sum. As we do this process for every single pixel, it gives a blurring effect which much more authentically simulates the notion of putting your lens out of focus or something like that. But blurring is far from the only thing that you can do with this idea. For instance, take a look at this little grid of values, which involves some positive numbers on the left and some negative numbers on the right, which I'll color with blue and red respectively. Take a moment to see if you can predict and understand what effect this will have on the final image. So in this case, I'll just be thinking of the image as grayscale instead of colored, so each of the pixels is just represented by one number instead of 3. And one thing worth noticing is that as we do this convolution, it's possible to get negative values. For example, at this point here, if we zoom in, the left half of our little grid sits entirely on top of black pixels, which would have a value of 0, but the right half of negative values all sit on top of white pixels, which would have a value of 1. So when we multiply corresponding terms and add them together, the result will be very negative. And the way I'm displaying this with the image on the right is to color negative values red and positive values blue. Another thing to notice is that when you're on a patch that's all the same color, everything goes to 0, since the sum of the values in our little grid is 0. This is very different from the previous two examples where the sum of our little grid was 1, which let us interpret it as a moving average and hence a blur. All in all, this little process basically detects wherever there's variation in the pixel value as you move from left to right, and so it gives you a kind of way to pick up on all the vertical edges from your image. And similarly, if we rotated that grid around so that it varies as you move from some pretty demonic work, the idea there is to use data to figure out what the kernels should be in the first place, as determined by whatever the neural network wants to detect. Another thing I should maybe bring up is the length of the output. For something like the moving average example, you might only want to think about the terms when both of the windows fully align with each other. Or in the image processing example, maybe you want the final output to have the same size as the original. Now, convolutions as a pure math operation always produce an array that's bigger than the two arrays that you started with, at least assuming one of them doesn't have a length of 1. Just know that in certain computer science contexts, you often want to deliberately truncate that output. Another thing worth highlighting is that in the computer science context, this notion of flipping around that kernel before you let it march across the original often feels really weird and just uncalled for. But again, note that that's what's inherited from the pure math context, where, like we saw with the probabilities, it's an incredibly natural thing to do. And actually, I can show you one more pure math example where even the programmers should care about this one, because it opens the doors for a much faster algorithm to compute all of these. To set up what I mean by faster here, let me go back and pull up some Python again, and I'm going to create two different relatively big arrays. Each one will have 100,000 random elements in it, and I'm going to assess the runtime of the convolve function from the NumPy library. And in this case, it runs it for multiple different iterations, tries to find an average, and it looks like, on this computer at least, it averages at 4.87 seconds. By contrast, if I use a different function from the SciPy library called fftconvolve, which is the same thing just implemented differently, that only takes 4.3 milliseconds on average, so 3 orders of magnitude improvement. And again, even though it flies under a different name, it's giving the same output that the other convolve function does, it's just doing something to go about it in a cleverer way. Remember how with the probability example, I said another way you could think about the convolution was to create this table of all the pairwise products and then add up those pairwise products along the diagonals. There's of course nothing specific to probability.
All right, so I think we'll go ahead now. We'll probably come back to it if we want to implement convolutions from scratch. But I think we have a naive idea of what they are. Right, so convolution takes a kernel, slides it across the input, applying this kernel to each patch of the input. Yes, it imposes a prior of locality, and each output value should only be determined by a small patch of the input. Okay, makes sense. Let's look at this. We can compute the output dimension, size, the function of the input dimension, and convolutional parameters. Hmm. Okay, so why would convolutional layers be less likely to overfit data than standard linear layers? Well, overfitting is when you fit to the noise in the data rather than the signal. First of all, convolutional layers are more efficient on average, so you have less number of parameters uh, per output feature. Uh, and two, no, I think that's the main reason why it's likely it's less likely to overfit. Yeah, because you're not uh, considering every possible uh, for each output feature. You're not considering every possible input feature, and that's basically uh, followed from the fact that you have less number of parameters per output feature. Just looking at a small patch of the input instead of the whole input. Yeah, yeah, this makes sense. Suppose you fix some random computation of the pixels, oops, in an image, and apply this to all images in your dataset before training on CNN. Do you expect this to be less effective or equally effective? Hmm, I would expect this to be less effective because the the inductive bias of convolutions is to have a local uh, prior. The input pixels that occur together are supposed to be more meaningful. So if we do not have that, when we do a random permutation, we do not have that anymore. So I would expect it to be less effective. Yeah, yeah, you destroy locality. So you have a 28 by 28 image and you apply a 3 by 3 convolution, straight to padding 1, 5 per chance. Okay, let's see. I have a 28 by 28 image, a 3 by 3 convolution, straight to and padding 1, 5 output channels. So when you apply a 3 by 3 convolution, straight to padding 1. So you effectively have a 30 by 30 image, including the padding. And then you're applying a 3 by 3 convolution with stride 2. So you first apply from 0 to 0, 1, 2, and then you move to 2, 2, 3, 4, and then you move to 4, 5, 6, and so on until um, well 28, 29, 30. So that's about 15 rows and columns. Yeah, but you have 5 output channels. So you get 5 cross 15 cross 15. Is that correct? 5 cross 14 cross 14. Okay, let's see. Um 14, shall we go from this to this? But does the padding not make any difference? If we use this formula, it's 28 plus 2 times 1 minus uh, 3. So that's 27 by 2 plus 1. You have 13.14 get 14. 3 times something. Okay, is this what padding 1 means? Okay, then I misunderstood what padding meant. Thought padding would mean you add zeros on all sides of the grid, all sides of the input. So it's not 28 by 28. What you get is 29 by 29. So you go from 0, 1, 2, 2, 4, 2, 3, 4, 4, 5, 6, so on up till uh, 20, 26, 27, 28. And this means 26 by 2 is 13. So you go from 0 to 13. So that's 14 height and 14. Yeah, it's 14 height and 14 width. Think makes sense. Wait, this is. Yeah, okay, we have our first exercise. So we don't implement it from scratch, but we'll use this functional implementation of conv2d. Fill in the init method. So this is the shape of weights, but what's groups? What is groups? Do we have groups? No. Default it's 1. So for each pair of input output channel, you have a kernel. The size is given to you, and the values of weights are sampled from uniform distribution in this, where k is 1 by number of input channels times kernel size for each dimension. Okay. Uh, so this would be what we need. And so I don't think we use the product of input channels and kernel header width for our initialization bounds. I think we want it to be normalized across the output channels. Uh, that must be why. Usually the output is computed by taking the product over elements. Hmm. Yeah, I think we'll let this run. Meanwhile, just a question about channels. Incorrect. Wait, initialization. Oh, yeah. Let's look at the solution. Okay, so scaling factor. Hmm. And now if we do max pool, I don't think there's an exercise here. We often add a max pool layer after convolutional layer, responsible for reducing. Hmm. All right, let's do ResNets now, I guess. What's part of ResNets? We have patch norm, and we have a bunch of other things. Guess, yeah, let's do a bit of this. Yeah, should move on and see if we can answer the following questions. is to be less careful about initialization. Well, that's because patch normalization is taking care of the mean and standard deviation of the features that are going into the feeding into the next layer. Uh, Specifically, it's trying to keep them uh, like something like 0 and 1 or beta and gamma. So we'd have to worry less about how the weights are initialized. Even if the weights are, let's say, very huge, in that case, if you do batch normalization after that layer, then it sort of alleviates the bad initialization of weights. Yeah. I guess we've seen them in this post. It's basically it improves the learning speed. It improves access regularization. Uh, and what was the other one? Yeah, I guess that's the main reasons. Internal covariate shift. Hmm. And finally, if you have an input tensor of size so and so and you apply batch norm layer, how many learned parameters will be there? So I guess the key question is, do we have a separate uh, learn parameter for each channel? No, I don't think so. I think it would just be two learned parameters. It's calculated for each channel. Mm, let's look at this section. Yeah, I'm not sure I understand this part. Do we have separate? Hmm, I need to come back to that. Uh, So in the paper, the diagram shows additive skip connections. So form concatenated skip connections. Key one advantage and one disadvantage of these relative to additive connections. So one advantage of this over additive connections could be that these signals are decomposed, uh, and if they're tracking different features, those different features stay separate, and that could be useful for downstream layers to do some task. And but the disadvantage could be that it's mostly the the activations keep getting bigger and bigger in terms of size, uh, because you keep concatenating them, and and the activations are not that dense. If they're sparse, then this um, in total they become even more sparse, and this it's really hard to, it becomes inefficient is what I'm trying to say, I guess. But also they don't compose as well. For example, layer 2 can undo what layer 1 did if we have additive skip connections, by writing the negative of that. But if you have concatenated skip connections, you can't do that. Yeah. Let's see what have they given. Subsequent layers can reuse middle representations. It still works if the tensors are at exactly the same shape. Yeah. Less compact, so there may be more ways to learn. Hmm. Okay. Yeah, I'll just run this and move to the next part. So we'll implement batch norm, implemented according to the PyTorch documentation. The primary function is to normalize the activations. I'll just be back. Yeah. So I guess, hmm, let's look at the docs first. Yeah. So let's calculate the mean and variance. So the mean would be, And now we will calculate the running mean. And how do I update something from the buffer? And finally, to return. But this is for training. You also have to handle the case when you're doing inference. Uh, yeah, can do this. Do is this should work. Okay, let's see. Okay, this doesn't. Okay, there's too much difference. Oh, my bad. And similarly, if I do this, Now batches track. Yep, makes sense. Let's see. Yeah. Hmm. Makes sense. Okay, let's finish this. Okay. Yeah, I think I'll stop here and yeah, we'll continue from here in the next video. And yeah.